Okay, so it's 4:30 UTC, so let's start. Yeah, I'm going to have to reiterate what Rod said. It's got a good showing. And yeah, so let's get started. First things first, the session is being recorded, FYI. If you have not, please, somebody's asking me to disable the bleeps. Does anybody know how I do that? I have absolutely no idea.
I didn't know that was possible. If it's possible, that would actually be useful. But as far as I'm aware, it's not.
So this is the first time I use WebEx, so I have no idea how to do that.
You can only disable them when you set up the
Option
meeting.
somewhere. Yeah, exactly.
Yeah, and once the meeting started, you can't change the settings.
Oh, that's a shame. Well, that's a lesson for next time. It won't be happening for longer.
Okay, Wojtek, why don't you and I introduce ourselves just so people make sure they know who is who. I'm a leader from Keio University, and I'm one of the co-chairs. That's me. I'm going to mostly keep my camera off to save on bandwidth and whatnot, but that's me. Say hi. Right, and Wojtek is our new co-chair, and he's actually going to be doing most of the running of the meeting. Wojtek?
Hi, everybody. Yeah, thanks for that. I'm Wojtek. I'm currently a postdoc at QTech, and I have taken over from Stephanie as co-chair to help Rod with running stuff. And yeah, I'll just do the boring running of the meeting, and I'll be keeping the timer on things. Rod might have to take over in the second half of the meeting when I will be presenting. Yeah. Okay. Thanks for that. So, start with session is being recorded. Please switch off your video to save bandwidth. Mute your microphone unless you're speaking. And a convention during these WebEx meetings is to, if you want to ask a question after a talk, write +Q in the chat, and -Q if you want to remove yourself. And the chair that's currently running the meeting should be monitoring the chat to do that. The Jabber is on, and I have one request to everybody. Is somebody willing to take the minutes for this meeting?
I'm willing to take that.
Okay, thanks. Can you take to take the minutes, you can take them either on your own editor, or you can use the Etherpad. There's a space for minutes there if you want to make them live. Okay, and just send them if you don't do them in the Etherpad, send them to me and Rod after the meeting, or to the mailing list. Cool. So that's in terms of the practicalities. There's the IETF Snowdwell. It's the usual. I don't think there's anything to dwell on here, unless somebody wants to mention something specific about the Notewell.
Hi, nothing specific, but there is an IETF one which is subtly but different, so nothing important.
Oh, good to know. I just copied the one that I found on the advice for working groups. So I will know for next time. Now, okay, so let's start with the meeting. The agenda for today is packed, so let's try to stick to the times, and I'll try to closely monitor that. We will first start with some administrativia and a brief RG status update. There will be then a slot to talk about simulators, as there's been quite a lot of attention about that on the mailing list lately, with 2 releases and 1 coming out soon. And there's a talk volunteered by Nathan Aw about quantum internet and its implications on the existing internet applications. And then we'll have half an hour slot to talk about the 2 current drafts in the working group. So first update is, there's only a small update, which is that we are now a full IRTF research group, updated from a proposed research group. Can everybody who's on mute themselves, please, if they're not talking? So we have been upgraded to a full research group. Thanks to Rod and Stephanie for getting this running. Basically, for each research group for a year functions as a proposed research group to see how they function. And we've been reviewed and we've been upgraded to a full research group. And as a brief summary of the history of what's going on and what's kind of going to happen in the future, is the idea originated in 2018. Rod presented the IRTF Open in March 2018. Approved as proposed research group in November 2018, and now we are a full research group. Originally, there was a tentative proposal to meet once at the IRTF/IETF meeting, once at a quantum conference, and once virtually. So I guess we're achieving that once virtually for the first time, though we did have some interims before to work on a draft. Me and Rod will reevaluate that over the coming few weeks and might consult the mailing list as to how best to actually meet as a research group. So far, we've been kind of doing the IETF meetings quite well. That's all there is for an update from me. Rod, do you have anything to add before we move on to presentations?
Only the administrative bit of there are now 56 people in the WebEx conference, and only 28 people have actually signed in on the virtual blue sheet. For those of you who came in a couple of minutes late, on Wojtek's very first slide, the chair's very first slide, there's a link to the Etherpad. Please sign in there and put your name in the blue sheet so that we have a list of people who are attendees. That's it.
Okay, thanks. Yeah, so the link's now in the WebEx chat. And apparently, if you're behind a restricted firewall, you can remove the 9009 port number. Okay, so first speaker up is Axel. Is going to start with the first simulator. The order of the simulators is based on release date, FYI. So we start with the ones that were released earliest, and we'll progress to the ones that will released or will be released latest. So Axel, are you ready to share your screen and present?
Yes, thanks. Can you hear me?
Yes, we can hear you.
Great. I'll start sharing my screen. All right, can you see my screen?
Yeah, I can see your screen.
Oh. Okay, is this, so can you see the slides and hear me well?
Yes, I can.
Okay, great. All right, thanks a lot, Ronnie and Wojtek, for organizing this. I think it's really great, and I think it's a really nice opportunity to see the different simulators that we have around the world and have the chance to present these. So I'm going to talk about Simulacrum, which is a simulator for developing quantum internet software, which been around now for, I guess, a bit more than 2 years, roughly, and was originally developed by me and Stephanie at QTech in Delft. And I would like to kind of spend this talk on more describing what our view of Simulacrum is and what we see its purpose and kind of how it fits into research and what you can do, rather than maybe focusing on technical details of how you use it and so on. So you can of course find in the documentation, and for example, other talks. I gave a talk at FOSDEM this year, which you can also still look at, where I gave a demo of how to use it. But maybe to get going, so to kind of set the stage a little bit of what simulacron is, I would like to kind of zoom out a little bit and explain why we developed simulacron, or where we're coming from this. So at QTech, we're trying to build a quantum network between at first 4 cities in the Netherlands. And we don't just want to build kind of a small fixed network. We're focusing a lot on how to scale up, or how to design a scalable blueprint for a large-scale quantum network, so that we can go further and span the Netherlands and Europe and maybe further. So things that we're doing to enable this is, one thing is in particular is to bridge the gap between an application, or how you design or think about applications for quantum network, and the hardware. And one of our main projects in this area is developing what we call QNodeOS, which is an operating system for quantum for nodes in a quantum network. And this is kind of a bigger project involving a lot of people here at QTech. Also, Wojtek is involved in this. And this is kind of a large thing, and I won't have time to go into the details here. But for example, what I would like to mention is that if you would like to write an application for a quantum network, what you is interested in is how do you communicate with this QNodeOS? Like, how do you write an application, and how does it then talk to QNodeOS? Essentially, what's the interface between the application and QNodeOS? So we had a proposal for such an interface. We call it CQC. It's for Classical Quantum Combiner, which we developed kind of in parallel with simulacron. Over the years, we kind of realized a lot of things and learned a lot, and realized that maybe how we initially designed this interface is maybe not ideal for what we actually want to do. So during the past time, we worked on improving CQC. Yeah.
Excellent. Have you been advancing the slides by any chance?
I'm in for need for QNodeOS at the moment.
Oh no! So people have pointed out that your slides are not advancing for some reason.
Oh.
Do you want to try resharing your screen?
So
Probably shared the PowerPoint application and then you went full screen, and that window's not shared.
Oh, so you don't see the full screen?
We don't see the whole window yet, the right window.
It's your browser.
You shared your app before you went full screen, so we see the app behind it, not the full screen.
Oh, I see. Okay, sorry for this. Let me see if I can. So do you now see a slide in full screen
Yes, we do.
that says need for QNodeOS?
Yeah. When you advance the slide, can you let us know so that we can check if it's actually advancing?
So is this, do you see slides changing?
Yeah, seems to work.
Okay, okay. So, oh, shit. Sorry. My bad. So sorry for this. Okay, let me try to. I can show you briefly the slides that I intended to show. Here's kind of upscaling to a quantum network. We want to bridge the gap between applications and hardware. And we had this need for an interface between applications and QNode-OS. And let me maybe double check if this is working now.
Yeah, it's working.
All right, thanks. Yeah, as I said, we realized that maybe CQC is not exactly what we want. So we worked on a new version of this and took some inspiration from QASM, which is a quantum assembly language, or there are multiple flavors of it, mostly used for quantum computers. And we kind of designed or started designing something using ideas from this for networks. And now there's some fancy animations where this new interface, which we call netQASM, comes in and kicks out CQC. So netQASM is essentially a quantum assembly language for networks. And again, so the idea is that netQASM is essentially the way how you would interface if you write your own application to the actual network that we're building and also later expanding in the future. And netQASM is something that we're working on at the moment. And I won't have time to go into the details of this, but it's essentially a low-level instruction set architecture for quantum internet applications. And this is something that will hopefully, in the near-term future, we'll can say more about this and kind of announce exactly what it is. But this is something that we're working on at the moment. And so this is kind of the end of the introduction of where Simulacron fits in. So when we had this CQC interface and we talked about how an application connects to the quantum hardware, it's kind of at the moment we don't have such quantum hardware, but you might already now want to write an application. So this is exactly where Simulacron comes in, where we had essentially a library, for example, in Python, where you can easily write an application that communicates with Simulacron over this CQC interface. But as I mentioned, we're now kind of changing this to this new netQASM interface. And in CQC, we also had multiple libraries in different languages. For example, we had in Rust, which Wojtek made. We had in C, Java. There was someone also working in Go, which is not, I think, fully finished. But you could write your application in any of these languages, and it would communicate with Simulacron. But not only Simulacron. We also want to be able to communicate with other simulators. For example, we have a kind of a beta version of this with NetSquid, which Rob will present a bit later today. But of course, also in the future that you will be able to use these applications you write today to run on real hardware. And maybe I can do a time check. So how much time do I have left, actually?
You've got like 1.5 minutes left.
Okay. So then I'll speed up a little bit. So one thing that's I think is really cool about Simulacron is that it's actually a distributed simulation. So you can install it on different computers. And these computers can together simulate the quantum network, where, for example, entanglement is essentially simulated by, in the background, essentially classical messages to enable this. And maybe just to finish, and then maybe there's time for maybe one question, I just want to say that if you want to get started, it's very easy. You just pip install Simulacron, and then you can start it, where you have essentially a daemon running on your computer, which you can communicate to using CQC that simulates essentially quantum hardware. And if you want to know more, you can go to our website where you can find the documentation and try it out for yourself. So that's it for me, and I'm happy to take any questions now or later after the meeting.
Thanks, Axel. We don't really have time for questions. I'm going to be quite strict on time because we've got a packed schedule. If you have questions about Simulacron, Axel is on the mailing list, so questions can go to the mailing list. Okay, thanks for that, Axel. Next
for the
up
hiccup.
is Stephen. No problem. Next up is Stephen with QNetSim. Stephen, are you online and can you share your screen?
Yeah, just a second. Let's see. Is this working?
Yeah, I see your screen. Can you just change slides so you can see if that's working? Change slides, change. Okay.
Perfect.
10 minutes now.
Okay, thanks. All right, so I'm going to present our quantum network simulator that we've been working on, and it's called QNetSim. So the the talk is basically a high-level overview of what it does and how to use it. So what is it? It's also a Python framework, and we use it for developing simulations of quantum networks that have classical and quantum connections. So how it would work is you have hosts in the network, and the hosts are sending messages between each other, go up to this quantum network cloud, and things are happening in the quantum network such that Alice can perform some kind of protocol, and Bob receives it, and it gets routed through a quantum network where the hosts are kind of oblivious of how this information is moving around to some extent. And then, yeah, so a summary of kind of its features is it simulates the network and application layer of a quantum network. So therefore, it's also looking into the routing algorithms and stuff like this. It simulates a multi-node communication network where each node processes classical and quantum information. So this means that the hosts can transmit classical messages, they can transmit quantum information, they can transport like EPR pairs and all these quantum objects as well. So QNetSim is composed of 3 components, and these are the host and the network, similar to an OZ layer style with the first 3 layers or so. I guess the top 3 layers. And the way this works is the way these components work is that a host is acting like a node in a network. So they perform kind of applications and things like this. And they can also process and store quantum information. So they have some memory which can be addressed, and this kind of allows them to hold on to information if they need it, and then protocols can be designed such that one knows that the information that they previously sent is stored at the other side. Yeah, so the host can act as 2 types of hosts, where one can be an end node or a relaying node. An end node is one that runs an application and or receives information and stores it. And a relaying node is a node in the network that just takes the packets that come to it and relays them further in the network. And they can also be programmed to perform attacks on these packets. They can run, each host can run a custom protocol. So you can write a Python function and then assign it to a host, and then the host runs this function asynchronously, or it can also run it synchronously. And here's kind of a small picture of what a host looks like in my mind. It has 2 processors, one for classical, one for quantum, and it has 2 storage devices, one for classical, one for quantum. So some of the built-in protocols that come with these hosts are basically quantum teleportation, super dense coding, EPR generation, GHZ generation, key distribution. What this means is that we have a host object in QNetSim, and the methods of the host are, for example, I can create a qubit, and then I can say host.teleport qubit to receiver. And these kind of tasks are all built into the host object so that we can recycle them and build more complex protocols on top of these. And also the synchronization and things like this are all handled by QNetSim, so that kind of these complex software tasks don't need to be handled by the user, and they're handled in the backend. Another thing is that they have these addressable quantum memories so that they can synchronize themselves when they're performing maybe a multi-step protocol. We have this transport layer. So the transport layer is responsible for taking the application data, packetizing it, and then puts it into the network. but it also is responsible for making sure that if the protocol requires an EPR pair ahead of time, that this EPR pair is generated, so that if you want to send a teleportation, but there's no EPR pair generated, it will generate this EPR pair ahead of time, or one can get warned that there's no EPR pair and then it's not possible to run such a protocol. So here's my picture of what the transport layer is doing. So the host is wanting to send an EPR pair. This goes through this kind of transport layer where it packetizes everything and then it gets put into the network. So the third component, therefore, is the network. And the network is responsible for connecting hosts through multi-node routes. So one can construct a complex network, and I can take a host and say, send a teleportation to a node that is maybe not directly connected, but the network will be responsible for moving this packet in the network, just like any other network in the classical internet. And it can be programmed so that one can design routing algorithms on top of it. So maybe there's an approach to routing for quantum networks that requires something novel, not just shortest path, for example. One can test these things in these networks. And then we can kind of add parameters to the network so that they have noise. They can apply errors to the qubits that are being transmitted, and they can randomly drop packets. Also, when we want to establish entanglement between distant nodes, we should have, in place a multi-hub entanglement swapping procedure that happens. So we have this kind of picture where Alice is sending her EPR packet. It gets packetized by the transport layer, goes into the network, who is Bob, in between the Alice and Eve. And Bob relays this packet, and then Eve receives it, and then Bob is performing also an entanglement swap. And in the end, Alice and Eve are sharing an EPR pair. So the pros and cons of using Simulacron is that, QNetSim, is that it's very high level. The programming, the way we've kind of structured the code is it's built upon a classical internet stack, and all of the functionality is very kind of straightforward to use, I think. We can program many network scenarios, so we can quickly change the network setting. We can add and drop connections. We can, put noise in the network. We could take noise out. We can have memory. We can have all kinds of configurations for this network, and we can use it to test routing algorithms. That's an interesting feature, I think. And there's lots of logging messages, so that if I'm wanting to write a protocol and I'm not working, I can see step by step what's happening in the network. And since we have this layered structure, we can kind of see what's happening, so we can more easily debug. Now, the cons of using it is that the channel models are relatively simplistic. These error models are kind of just X error, Z error, and maybe not enough noise to represent a physical system. When we are increasing the scale of the network, things tend to get a bit slow. And it also is assuming that the quantum internet is based on a packet style where there's this transport layer in between and things like this, where maybe this is not something that will happen right away. So the people who I think should use QNetSim are beginners who are just learning about quantum networking. Because of this high-level simulation framework structure and stuff like this, it's easy to kind of go from a classical setting to a quantum setting. And therefore, instructors can also use this to teach, because it's very analogous to classical networks. And researchers can use it in a way that they will test their developed applications for robustness and correctness as a first stage. So maybe they can't benchmark if their protocol works under all kinds of scenarios with some kind of rates, but they can test that at least it works in some kind of basic scenarios as a first stage. So just, if I have time, show a quick example of how it works. We would define some protocol, and in this particular protocol, the sender is just sending 5 EPR pairs to a receiver. So I write this function, protocol 1, takes a host and it takes a receiver. Then I run a loop 5 times. I send an EPR pair on line 12. What happens is, because I set this flag here to await ACK true, this line of code will block until an ACK is received by the person sending it, and then we can perform operations depending if the ACK arrived or not. And then we have our qubits who have an ID, and we can kind of perform operations on this qubit by fetching it out of the memory. Where on line 17, we see that the host is fetching their qubit by ID. And then on the receiver side, we see that this function takes the sender ID, basically waits for 5 APR pairs to come. So we see for this loop here, and we set this flag here, wait for 5, and this means that the host is sitting idle, waiting for the EPRs to arrive, and then it just performs a simple measurement to determine if the EPR was a legitimate EPR pair or not. And then what we do is we construct a network. We have this network singleton object. We define the nodes in the network. We define the node IDs, and then we have these host objects. These can be, we can add connections to the hosts, and then we put all the hosts in the network, and then you see these 2 lines at the bottom. We can run our 2 protocols that we defined above. I think I'll skip the next example, but it's basically how it would.
Can we just wrap up now, Stephen?
Yeah, sure. I think this is the last slide.
Yeah, there seems to be a question on the chat, but please take it offline to the mailing list or on Jabber, if you're on Jabber. So thanks a lot, Stephen. Next is Rodney presenting QISP. So yeah, Rodney, do you want to share your screen then?
Let's see if I can make that work. Hang on, pull up the right window here. Let's see. Where's my Chrome? Tell you what, we'll do it this way. There we go. You see it?
Yeah, we see it.
All right. Let's see if you still see it. If you've still got me when I switch into presentation mode here. All right. You got the.
Got you. Yeah, and slides change. Go ahead. Okay. 10 minutes.
So we have just, as you have seen on the mailing list, announced that QISP is available open source. There's a link to that there. QISP is the quantum internet simulation package. Here's a partial screenshot of one of the larger networks that we're in the process of simulating. If any of you have worked with OmNet++, you'll recognize the style of icons and whatnot. QISP actually builds on top of OmNet++, which means that, of course, all of the code is actually implemented in C++, as opposed to most of these other simulators that are written in this modern language called Python. So we're designing QISP to answer a series of research questions. And the first one is, we're looking for emergent behavior. What's the equivalent of quantum the quantum equivalent of congestion collapse, for example? We're also working on protocol design. The basic architecture we have laid out is what we call the rule sets that are based on a condition clause and an action clause, like SDN match action seems to be sort of the more common terminology. There's a lot of emphasis in what we're doing on the classical messaging and studying where the latencies occur in the system and attempting to eliminate those. So far, that's pretty similar to what the other simulators are working on, I believe. But one of the things that we're working on that's rather different is that we're studying not just first generation purify and swap networks, but also second and third generation networks, and hopefully studying both logical and physical heterogeneity, including also dynamic behavior such as link state changes and traffic pattern changes and whatnot. So very quickly, there are 3 generations of repeaters that have been defined. The first one, which I've already alluded to, uses quantum purification, which is essentially error detection, and uses entanglement swapping to build the end-to-end connections. Second generation uses quantum error correction instead, which means that the states that are used are actually larger. And third generation is similar to second generation. The difference between second and third is that in the third generation, photon reception is very high probability, and therefore you can go with a more of a store and forward kind of approach rather than the end-to-end entanglement swapping that has to be done. And these were defined by Liang Zhang's group, and there's a link there if you're interested. So I listed here, I'm not going to try to go through this entire slide, but I thought it would be useful for people in the group to who are not as familiar with the quantum computing world to understand a little bit about how the different possible ways of writing down quantum states are. A lot of noise from somebody. Wojtek, is that you or is that somebody else?
Yes, but I'm trying to mute these people when I hear them.
All right, thanks. A lot of the most simple, the first thing you learn when you're studying quantum computing is the basic state vector approach, usually using what's called Dirac's Ket notation. You can see the scaling of it there. We're actually working in what's called the error basis, the last line there at the end of the slide, in which we're only tracking internally whether or not the state corresponds to what we're actually trying to build. So we're tracking, we have in the simplest form, bitwise flags. Has there been a bit flip on a particular qubit, for example? And that gives, as you see in the right-hand column, essentially linear scalability in the overall simulator. Why is that a big deal? Well, if you look at this, if you are trying to write down an entire quantum state, and you're studying the physical processes, including error processes, what you need is the density matrix representation, which was developed by John von Neumann, which is a name probably everybody here knows. If you have 2 qubits in your state, the size of a density matrix is only 128 bytes, assuming double precision floating point numbers for your complex amplitudes. But it grows pretty quickly to 256 kilobytes for a simple representation of a single error-corrected state at bell pair of 2 qubits. But if you want to even just take 2 of those and combine them, all of a sudden you're all the way up into petabyte scale sizes for memory. So it's simply not feasible to simulate a large-scale quantum state that's entangled across multiple nodes when you're involving quantum error correction and whatnot. So all of this led us to working in the error basis instead. So the strengths of what we've got, scalability is the ultimate target. Our goal is to simulate a quantum internet, not just a network, but a network of networks consisting of 100 networks of 100 nodes each and probably 100 qubits per node. So on the order of 1 million qubits. And all of this is made possible by working in the error basis. As Axel's already alluded to in his system as well, one of the things we're very interested in is the development of software for the repeaters and the routers themselves. And so you'll see a diagram there that shows our internal structure for how the modules fit together. There is absolutely endless configurability in this, building off of Omnet's capabilities. And it provides animations and an inspector for the state and lots and lots of logging and tremendous capabilities all built into an IDE. If you've used Omnet, it's actually incredibly powerful. So the weak points for what we're doing, this is not tuned for very low-level simulation of the physical processes, although we do have a model of both Pauli errors, which are symmetric errors, and non-Pauli errors. Installation is kind of a bit of a pain, mostly because installing Omnet is a pain in a variety of places. And there's a lot of stuff that's actually in development. Although this is actually already our 4th generation simulator internally, where the Thaddeus Lad, who's in here somewhere, built the first one, and then he and I worked on the second one, and then a student of mine worked on the third one. And now this is our 4th time around for a quantum network simulator. I just tossed in a very brief summary of what I think the basic goal of the 6 different simulators that I know about here, and this is not intended to be sort of definitive, but hopefully to give people sort of a basis for discussion later, which might actually be a topic we might want to take up on the mailing list would be sort of a comparison. We might actually be interested in building a document for doing all of this. And there are the links. Come join us, clone away. The software is on GitHub. Join us on the Slack if you're interested. And the best resource for learning about it is Takaaki Matsuo's master's thesis, and there's a link to that there. Wojtek, that's it. Thanks.
Thanks, Rod. We'll actually have time for questions. If you want to ask a question, please add +Q to the chat, and then I'll call your name out.
I'm happy for us to not take the questions and go on to get us back on the time schedule so we finish up. That would be fine.
We're mostly on schedule. But yeah, I see there are no questions. There's always the mailing list. Can always keep the discussion going there. So next up is Rob with NetSquid. Rob, are you ready to share your slides?
Yes, can you hear me okay?
Yeah, I can hear you, yeah.
I see the application sharing is in beta, so I hope this works.
I have your slides as a backup anyway, so
okay.
It doesn't work. Yeah, we see your slides.
Okay, I don't, so I'm gonna have to change window. You see them? And you see the slides changing?
We see them changing.
Cool, okay. So yeah, I'm Rob, and I'll be presenting the NetSquid simulator on behalf of the NetSquid team at QTech. Well, page down, yep. So NetSquid is an acronym for Network Simulator for Quantum Information Using Discrete Events. And it's a project that's been under development at QTech since about 2017 as a collaboration between TNO and TU Delft, which are sort of the partner institutes in QTech. And it's been actively used within QTech already for that time by the groups of Stephanie Werner and David Appes, so the theory groups, and also already a bit by some of the experimental groups in the QIRG roadmap, so the Quantum Internet and Network Computing roadmap of QTech. And for the last 1.5 years also by some of the partners in a European project called the Quantum Internet Alliance. So that's, yeah, the past 3 years has been essentially private use. But yeah, essentially this month, or actually last week, we were planning a public beta release. It's been delayed, unfortunately, by hopefully only a week, as we're still trying to finalize the user license. So very soon, we're hoping to provide this publicly, so a beta anyway. So watch this website for more information. To sort of explain what NetSquid is and how it differs, I think Rodney already explained that in his last slide. So to go in on that, how it differs a bit from the other simulators, it helps to sort of highlight one of the problems it tries to solve. So if we consider the quantum internet, it's essentially an infrastructure for sharing quantum information, and it's made out of all this physical hardware, quantum channels, fibers of free space, and quantum memories. And this is one way to move this quantum information, but really the key resource in the quantum internet, you could say, is quantum entanglement, which is acting as a virtual quantum channel between these nodes. And this resource has two properties. It has a sort of the rate you can make it at and the fidelity, or its quality. And in any sort of realistic network, both these properties are affected by non-ideal hardware, so lossy or noisy quantum channels and quantum operations at the nodes. And so one way to mitigate this when designing or building a quantum internet, especially as Rodney mentioned in the first generation of a quantum internet, is to use methods such as entanglement purification to deal with noise, or quantum repeaters to deal with loss. So very briefly, entanglement purification means that you can make multiple copies of this entanglement between two nodes. You can use a stochastic protocol such as distillation to increase the fidelity of these low fidelity links to sort of output, and you can nest this process to get a higher fidelity, and therefore deal with the noise that way. And to deal with the loss, so if you've got exponential attenuation across your quantum channels, you can start inserting nodes to shorten these links between your nodes, so-called quantum repeaters. And these can first establish entanglement, and then you can swap that entanglement at the repeater node. Now, the key element in these protocols for mitigating these effects is timing. So these purification protocols are generally stochastic in nature. And for example, if you're trying to perform this repeating, it may be that one arm will succeed sooner than the other, and we'll have to wait for the other one. And in that waiting time, these qubits are waiting on memories and they will start to decohere. So this high fidelity you thought you had from your purification starts to decrease. And by the time you swap, your fidelity is maybe not optimal and you want to design a better protocol. So the key takeaway here is to design a quantum internet, you need to solve complex timing dependencies, and that was the inspiration for developing NetSquid. So NetSquid, in a nutshell, well, it's this package here. It's a Python package. So it's available as a Python package, but under the hood, it's using C, C++, and Python code where needed to optimize it. If you look at this stack of sub-packages, I'm just going to check the other window. I hear a lot of beeps. Okay, there's nothing. If you consider this stack of sub-packages, then it's sort of key package it's built on is this discrete event simulator. So it steps through time discretely with events, and then it will update all the quantum states depending on how much time has passed. And that way we accurately track the time rather than running in real time or in a distributed fashion, such as some of the other simulators. I should add, this is the same as on Net++. We have a specialized quantum computation library for the quantum network, so which is what we say qubit-centric, so sort of hides the details of the quantum states to the user, so you can really just focus on operating on the qubits locally at nodes, and optimized for repeated sampling. A lot of the NetSquid simulators we do involve sampling to learn something about the performance of your network or your protocol. And we also offer different formalisms, as Rodney and Axel also mentioned, the KET stable formalism, the density matrix formalism, but also the stabilizer formalism, which does scale well for a large number of qubits, with the trade-off that it doesn't have a universal gate set. It has the Clifford gates, but for a lot of quantum network applications, those are good enough. And then finally, another key feature of NetSquid is its modularity. So we offer a library of base class components that can be composed of different physical models and then be composed of each other. So you can make a heralded connection, which has quantum channel components and classical channels inside it, and a quantum detector. And then that is one unit that you can then sort of copy paste between different nodes. Okay, so that's the simulator in a nutshell. I guess I have 4 minutes. So what would you use NetSquid for? So as I tried to motivate, really its strength is actually modeling timing effects, so the performance of scalable networks and systems. That means you can use it to investigate the requirements and the feasibility of different networks and protocols, and especially also in different layers of the quantum OD stack. So both for the physical layer, but also moving up to the control plane. So how does classical communication affect the performance by introducing delays all the way up to user applications, which Axel showed. There's an effort to integrate NetSquid with this netchasm language to be able to talk all the way up to the application level. And it could act as an emulator also for future hardware setups. Also in this thing. So there's a few examples of where it's been used in these for these things already. So study performance of a quantum link layer protocol, and also in a European project which is designing a blueprint for a European quantum internet with heterogeneous hardware. There it's being used to do parameter optimization and benchmarking of these different hardwares, and for sensitivity study of repeated chains. Wojciech, how many minutes do I have left?
2 or 3.
Okay.
You want to finish before the 2 or 3 if you want questions.
Okay. It's almost done. So how do you get started with NetSquid? So the first thing you can do or should do is register at the forum that will give you a username and a password. And you can use that both to participate on the forum, but also to access the online documentation. And very soon, once the license is ready, to install NetSquid using the standard Python package installer. So here you see how you can do that. It's a matter of just adding the extra Python package index for NetSquid with your forum credentials. So I have to stress this won't work yet. Hopefully this will work within a week. It's just a matter of this license being finalized. And this license is free for non-commercial use, so not open source. I should add that this has been quite a high-level description of NetSquid, but if you look at the documentation, there's a lot more detail if you're interested. And then finally, so NetSquid is really intended as a base package for people to develop their simulations on. And what we hope to stimulate is for users to contribute to NetSquid with what we call NetSquid snippets. So Python packages that are created and maintained and shared by users. And here we really encourage that people share this open source. We already have a number of these packages available on our package server. So this also does dependency management. If we host these snippets on the server, you can say, I want to install this snippet, and it should pull in any other snippets that snippet depends on. For examples of snippets we already have available, modeling snippets, such as general components for a physical layer, specific modeling for NV-centered devices and atomic ensembles, to things like quantum memory manager or quantum program manager for components higher up in the stack. And to get started with the snippets, there's a template repository that will generate a snippet template for you. And there's more information available at the website. And that's it. Time for questions?
Thanks, Rob. Sadly, we don't have time for questions. As always, questions can go to the mailing list or to the Jabber room. We'll move on to the next talk. Thanks a lot, Rob.
Yep.
Nathan is next.
All right, let me share my screen. Share content. Can you see my screen?
Yes, I can see your screen.
Right, great. Okay, I'm presenting. Right, so I've full screen my page. Okay, hi everyone. Just this is Nathan. Would like to share with you some of this some of the applications for quantum information network and some of the promising use cases that from a practitioner I think that and the profound implications that this might have on the existing internet applications. Okay, so one of the things that struck me was the similarity between lasers and quantum information network, right? The inventors of the laser, it probably didn't anticipate its many use, right? And this is an article from the Smithsonian magazine, right? But today lasers are used to read CDs, barcodes, missiles and everything. So what is really exciting for me personally is, this can be we can see parallels being drawn, right, to what we are discussing in this forum. And what we are discussing today, the use cases, the applications might look very different from what we will see next time, right? The unknown unknowns, right? Okay, so yeah, just go on to the next slide. Okay, this is just an introduction of myself. Okay, so some of these promising use cases that I have just top of mind, it might be a pie in the sky, but I believe that scale out quantum computers will be one of the realities. Right now, many people, we just talk about, we are looking at scale up, quantum computers, and if you see the whole internet revolution and how computing has reached where we are right now in the classical sense, right? We have distributed clusters of servers, and I believe that, now with quantum computers, we might be, going back to the big mainframe systems, but in the future, we might see scale up quantum computers, leveraging, fundamentally distributed algorithms, right? Again, quantum algorithms are being worked on, and I believe that, distributed algorithms, will be, distributed quantum algorithms will be something that will be a reality sometime, right? And to perform many tasks, perhaps intelligent network routing. And one of the things that again might seem like pie in the sky right now, similar to serverless computing, what we see today, microservices and all, perhaps one day we will see, you know, a data center-less, you know, environment, right, where, you know, you have multiple quantum computers in the world, you know, driving all the workloads, right? Again, pie in the sky, but I believe that this is something that might happen, right? It will drive the cost of classical computing to negligible amount due to, you know, its sheer computing power. And of course, you know, we need to hook up these quantum computers together, right? And finally, perhaps zero latency networks, right? This is something that we often take for granted. Like for example, between the cloud servers that I have currently, you know, I see some latency, you know, 25 millisecond, you know, from the East Coast to the West Coast of the US, right? But again, perhaps, you know, in the near future, we could see zero latency networks, right, being enabled. Okay. All right, so I want to talk about the profound implications on existing internet applications. Quantum sensing is something that really excites me. You know, when all of these things that we discussed, they become a reality, I believe that many of these applications that we use today, they will be fused with this ability, right, to sense, you know, and to react accordingly, right? And applications that leverage quantum computation in its network will be able to respond so quickly, you know, that no classical computers or network could do so. And what is really important is as we see more and more internet applications, right, moving towards event-driven architecture, right, AWS, Lambda, you know, these serverless functions where they react, right, you know, I believe that this will lay the foundation for that quantum future that we might see, you know, quantum sensing internet applications. So this is one of the implications that we have, right? So some parting thoughts that I have, right? We cannot solve these problems with the same thinking that we use, right? So I thought that this is really a new frontier where we start on a new canvas, right? Without the constraints and limitations of classical computers and all the networking stack, you know, OSI reference model in mind. And of course, you know, in the process of trying to come up with the future, you know, we improvise, and from now to the future that we see, I believe that the outcome and all these use cases that we discussed, right, would be very different, and some of this will even be unexpected, right? Yeah, you know, in the industry that I'm working in, the financial services sector, right, quantum computing and its applications, we believe will have profound effect on some fundamentals, you know, underlying data usage and protection, right, and risk modeling, right. And specifically with quantum sensing, you know, we could record and measure, you know, some of these fluctuations in both time and space, and this could be further incorporated into risk modeling, right, and assessment. So, you know, very exciting if in that future where we have, you know, applications are able to incorporate these streams of, you know, data that's flowing in, right, you know, that'll be really, really exciting. So many things that I might share now, you know, might seem like a pie in the sky, but, you know, again, this wish list is something that I believe, you know, will become a reality in all our lifetimes, right? So that's for me. Thank you very much. I hope I reclaim the time. Okay. Yeah.
Thanks, Nathan. We actually have time for questions. So if somebody has a question, can you please put +Q into the chat and I'll call your name out.
2 minutes.
And Melchior, please.
Yeah, hi. So I'm just realizing now that I've here to help define the contract plane versus data plane part. And my apologies for not doing that earlier. And I hereby promise that I will send this week or at latest next week.
Okay. Any other questions? No, let's move on. Rodney, can you take over the chairing, please? Because I'll be presenting now.
All right, you're up. Excuse me. How long did you set up for this part? I don't have the agenda right on my screen here.
15 minutes for this draft and then 15 minutes for the next one.
Right.
Shared the wrong one.
We're actually running pretty much right on time, so you've got the full 15 minutes.
Oh, why is it sharing the wrong one? Give me a second.
feel free to share all of your internal secrets via the screen sharing.
Do you see Firefox?
Not yet. Yes.
Oh wait, you did, and I stopped the share.
While Wojtek is working that out, let me remind people who have not done so yet to sign in via the blue sheet on the Etherpad. Someone's been helping us straighten that out, so I think all the names are probably on there by now. MCR is Michael Richardson, I guess. All right, Wojtek, you're up.
Cool. Can you see my screen?
Yes.
So I'll be presenting the work that has happened since the last meeting on the architectural principles draft. In short, we're kind of moving now, hopefully, towards a close on it. And there's been quite a few updates since the last meeting. So first, a recap. The first version of the draft was prepared and presented at the IETF 104 in Prague on 26th of March last year. So it's just over a year now. My main motivation in putting it out was to address the first point in the charter, which was to have an architectural framework delineating network node roles, definitions, and to build a common vocabulary and serve as the first step toward a quantum network architecture. It's kind of evolved into being sort of kind of an introductory, a stepping stone document for people new to the field and who kind of want to try and understand what's going on and kind of presenting the outlook going ahead. So it was adopted at the IETF 104. It continued in a series of web call discussions in September, October, November last year before IETF 106. I received lots of feedback. A lot of people contributed. Basically, almost the entire document has been reworked. It's much more comprehensive now and accessible than it was at first. So thanks for all that feedback. And I do feel that the document is much better now. It's maintained on GitHub. There's a link. I share that link often on the mailing list. It's a public repository. It's just a convenient way to share updates so that I don't have to update the data tracker for every typo, etc. And that can basically, there can be kind of in between meetings live version. I do update the data tracker for the meetings though. But I don't do any of the fancy GitHub stuff. It's just there as a repository. So overview of the changes since the last meeting. I have two new authors who have contributed with the section on elementary link generation, which I'll go over in a slide or two. Bruno has contributed a comparison of classical networking, which I'll also go over. It's just a very interesting thought experiment, kind of outlines the necessary components of a network architecture. There's work in progress with Shota that contrasts entanglement swapping and classical forwarding, and some other minor updates and modifications. So what was this section about elementary link generation? So as you know, ultimately, we will want to perform entanglement swapping. To perform entanglement swapping, we need to have entangled pairs on the individual links first. So we refer to these often as elementary links. And this is actually a very physical process. It involves sending flying qubits, which are usually implemented as photons on a fiber. And the additional section kind of goes over briefly as to how you would achieve that. And there are actually a few ways you can do it. The key point in all of this is that it helps you understand how a node receives an entangled pair, because I think that actually was a question once asked on the web calls. And effectively, it's kind of, you need to understand the fact that when you entangle two nodes that are neighbors, there will be a heralding signal. There is a component in the architecture that will effectively know this entanglement has happened and heralds it to the nodes. And that's kind of how you receive. The quantum qubit itself doesn't ping you, but there is a component in the architecture that knows entanglement has succeeded, and it notifies you. There's also now a new section at the very end that pairs quantum networking with classical networking, most notably essentially an NPLS architecture. It's not a proposal for a network architecture. I find it a very useful kind of few paragraphs that for somebody who really understands classical networking can read that section, I hope, and get a good grasp of what is needed, what are the key components, what will be the key components in a quantum network architecture. It's kind of, after talking about all these qubits and entanglement swapping, how do we move to an actual network architecture? And I feel that section is actually a very good starting point, not by going through very tiny nitty-gritty detail about how you do it, but actually kind of just throwing out an idea that a lot of people here will be able to digest very quickly. And the benefit is it identifies a lot of key components of a potential network architecture in a very short amount of space. And currently, Shota has submitted a pull request on GitHub, and I've only just reviewed it recently. I was meant to leave it for after this meeting, but because of coronavirus, etc., I did review it before, but it's not made to the document. The point that Shota was trying to make is that the entanglement swapping way of distributing, the way we'll build this first generation of entanglement-based networks is that we won't be forwarding quantum packets like we forward normal classical packets. Entanglement swapping is in many ways different to forwarding, so we should actually probably just drop this forwarding. Rodney mentioned that once we get to the third generation where we can do error correction and error detection, we can actually implement forwarding. But that's not the way we'll be doing it for the first generation of networks. I hear some keyboard, and the keyboard person please mute. As an example, these entangled pairs are not directed. This is kind of one of the points made. So it's currently work in progress. It's on GitHub and not present in the draft version, and I'll be reviewing that and we'll be seeing how that evolves. All discussion happens through the mailing list anyway. So if you're on the mailing list, all the links to the GitHub should be present. So you can also, whenever there's an update on GitHub, there will be some ping on the mailing list that there's an update. So looking forward, what are the next steps? Well, first, I kind of wanted to have, and there was some feedback, I wanted to have more coverage of security, but I'm not an expert on this, and I've had no updates from anybody on this. So I was thinking that perhaps it's a complex topic that is not really suitable for an introductory document. And one potential option is to leave it as it is for now, because there is some coverage, very, very basic coverage of the security considerations. Add some references, and if needed, create a new document in the future that will be devoted to security. That's up for discussion. If people do want security in this document, then I will need some contributions in this section. Otherwise, I will leave it as it is. And looking forward, the key next step is to rework section 6, which is about essentially the goals and principles. This is kind of an open-ended section of the draft. It's kind of looking outward. What are the goals of a quantum network? How do we want to build them, and what principles? I've made a little update. I basically deleted everything I felt was more of my opinion, backed by science, but nevertheless, I left things that were basically definites. They're upgraded to their own section, and I was going to have a side meeting in Vancouver to have some community input. In the absence of that in-person meeting, what I will do is either wait for all the virtual interims to replace IETF 107 to finish, and then have a virtual meeting done, or I'll just continue discussion on the mailing list. I'd prefer it to be a meeting where people can talk, simply because it's just faster, and the mailing list may supplement that. Other modifications I will need to add is add references. There was a bit of discussion about what's the right amount of references for the document. And the consensus seems to be more than currently there I've put in, but let's not go overboard. And after all that, I will also plan a final editorial rundown Rodney sent an email with a bunch of feedback at the beginning of March, and I'll use that as a starting point to do this final editorial rundown. I would like to finish this draft by the next or after next IETF, in the sense not be actively working and hopefully submit it as an RFC. We'll see how that goes. So that's about it for me, and I'll open the floor to questions.
Okay, any questions? Anybody, you can put plus Q into the, yes, Matthias. Go ahead.
I have a couple of questions. The first one is, it's the second time you mentioned that in upcoming generations you could have forwarding. Do you mean that you would teleport qubits over each elementary link one after the other? Because that doesn't look like very efficient. And the second question is related to the structuring of the architecture in planes and probably layers. And for the moment, it's described in the other document in the use cases, but actually it would be more suited into this document.
Right. So the first question, I'll actually. So there's the first generation network is based on entanglement swapping. Whether it's less, so ultimately, once we have error correction, yes. I don't know if teleporting hop by hop may be less efficient. It will definitely be simpler. And potentially not require establishing circuits, because if you're doing entanglement swapping, the current hardware requirements effectively require you to establish a circuit, which means resource reservation and stuff. So forwarding might be simpler in that context. I'm not an expert on anything beyond the first generation, so I don't know if Rodney wants to add something to that answer.
Second generation will still work on entanglement swapping, but it operates at the logical level on top of bell pairs that are created across the link that are encoded in a QAC, a quantum error correction system. Third generation is the one that gets you real store and forward, but that requires photon reception probabilities of greater than 90% or something, which is way, 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 way far in the future. All right.
Yeah.
Sorry.
The second question.
Okay, go ahead. And then there's one more. Then there's one more in the queue.
Okay. So the second question about layers and stuff. I intentionally am avoiding layers, and there is a mention of planes, I think, in the current document. I avoid it for a good reason, because we had some because there's currently a tendency for everybody to literally map the classical network stack to the quantum network stack, and I do also want to avoid this principles draft being an architecture proposal, more of a informational document. And as soon as we put layers in, I think that becomes too close to a proposal for my liking for that document. So that's kind of why.
Okay, share that.
Okay, Gyan, you're up. Question?
My question was, how well these network simulators, comply or tested on our draft actually?
Well, the draft is kind of just open-ended and kind of just like an introduction. But in principle, you could use any of those simulators to simulate. To basically, what you should be able to do, as anybody actually on this call, you should be able to take this draft, read it, and hopefully understand it. And then take one of those 4 simulators and just start playing around with it. And that's it. And you should be able to start, create a protocol, try and have your own data link protocol, or implement the link layer protocol proposed in a paper from last year's SIGCOMM. Implement your own end-to-end connectivity, implement your own routing protocol. So that's kind of what you should be able to do.
Let's see. I think we have about 1 minute here. Colin Perkins is in here. Colin, do you want to toss in any comments on what needs to be done to move this toward RFC?
I think you seem to be doing a pretty good job of putting this on track. So I have very little to add other than to say keep doing what you're doing.
No comments on procedural or deadlines or process?
I mean, the process is once the working group is believes it's ready, you send it to me, and I make sure it gets reviewed by the IRSG and do a conflict review of the IETF work. In terms of time frame, I mean, the slide suggests having it ready by 108, 109, which I guess is the end of the year, and that seems like a perfectly reasonable time frame. But I mean, fundamentally, it's when the group believes it's done.
Great, thanks. Wojtek, thanks. Let's move on to the next item on the agenda, which is the last one, I think. Draft Wang QIRG quantum internet use cases. Let's see, who's the presenter for this?
Right, me, Chonggang. I'm going to present this draft. Yeah, let me share my slides.
Good. We see your app there. Okay, looks like it's in full screen. Try changing the slide there. Yeah, perfect. Okay, go ahead.
Okay. Yeah. Hello, everyone. This draft basically is about the quantum internet applications and some selected use cases. So we were trying to focus on this topic. So this draft this document actually was initiated back in January. So since then, we exchanged the draft. We have received many good comments and feedback through the mailing list. And then currently, based on that, we generated the current version 05. We received many valuable inputs from lots of people listed here. So it seems like people are supporting this use case document from the use case and application perspective. The content. So the main content in this document basically has three major sections, like the quantum internet applications. We briefly introduce two classification categories, like by application usage or by the control and the data plane. For the application usage, so basically we say there are three categories, like quantum cryptographic applications and quantum sensor applications. Third one is the quantum computing applications. And in terms of control and data plane classification, this one there are a few pending comments we need to address. So this one is still pending about this control and data plane classification. So based on the classification of applications, then we selected a few quantum internet use cases by giving more details. For example, we have the secure quantum communications, and also we have the distributed quantum computing. Also we call the quantum computing with the privacy preservation or blind quantum computing. So after that, we were trying to add a section dedicated to general requirements, but this section is still in the early stage. Again, we got some feedback from many lists asking if in which level of requirements, for example, performance indicators or some high-level requirements we need to add for this section or not. So this is still there are some pending questions over there about the general requirements. So for the first class of for the first type of quantum applications, the cryptography applications. So we think it's kind of the category for using quantum information technology to ensure secure communications. Two examples given here is secure communication setup. For example, to secure the cryptographic key distribution between two or even more end nodes. Quantum key distribution, which is one of the approaches for doing for this purpose. The second type of this cryptographic application called a fast Byzantine negotiation, basically to use a quantum network-based approach to achieve fast agreement in Byzantine negotiations. This could be used for the financial blockchain scenario. The second type of the quantum application is called the quantum sensor applications. Means to use the quantum information technology for supporting distributed sensors or even IoT devices. Example will be like the network clock synchronization. It's not about the two nodes to synchronize their clocks. It's more about a network, a worldwide set of atomic clocks collected by the quantum internet to achieve a more precise clock synchronization. So the third one is about the quantum computing. So actually, the first type is communication. Second type is more like a sensor clock synchronization. The third type here, slide 6 on slide 6, is more like the quantum computing. Basically, to use the quantum information technology for supporting remote quantum computing facilities. For example, here we got two examples. The first one is the distributed quantum computing, and the second one is the secure quantum computing with the privacy preservation. And then we're going to give a little bit more details about those two types in the following slides. So given those three types of quantum applications, in terms of the real use case, we were trying to come up with those three use cases in following slides. The first use case here, we call the secure communication setup. Basically, for example, like two banks, they need to have secure communications for transmitting their important financial transaction records between the bank number 1 and the bank number 2. We assume each bank has a corresponding quantum nodes A and B. So for this purpose, their requirement is need to securely exchange a classical secret graphical key, which could be triggered by either bank number 2 or bank number 1. So figure 1 shown here, we just show it will be triggered by end user in bank number 1. So this use case basically need to have a secure communication setup. And then in the document, we describe some procedures using quantum key distribution 2KD as an example to show it can be used to serve this use case, secure communications setup. The second use case shown here on slide 8 is called the distributed quantum computing. So trying to say either in the near term or even mid term, we're going to have the noisy intermediate scale quantum computers called NISQ. They are going to be distributed in different locations. Also, they are available to be shared together. So ideal here is trying to use the distributed NISQ computers to get more powerful computing capability. But in order to gain this higher computing power, how to collect those distributed NISQ computers together, and how to reliably transmit or share the quantum bit states among those multiple middle scale or small scale quantum computers. That would be the the issue to be addressed. But use case here is trying to say there are many small computers, quantum computers distributed in different places, and we want to collect them together to have a more powerful computing capability. And of course, if the quantum computer A, for example, wants to say reliably transmit the quantum bit states from A to B, the quantum teleportation can be utilized for this purpose. Third use case here, we call the secure quantum computing with the privacy preservation. It also can be referred to called a blind quantum computing. So here, the use case here basically likely we have the quantum terminal node. If you look at figure 3, for example, a home gateway, and then they want to delegate some computing to a remote quantum node, which could be a quantum computer in the cloud. But here is they don't want to share the original source data, so they use here what we call the quantum computing with the privacy preservation. So basically, the quantum terminal node at home could sending some quantum bits plus some measurement instruction to the remote computing node. After that, the remote computing node can, based on the measurement instruction, do some computation on the quantum bits and send back results back to the quantum terminal node. So this case just shows the usage of the quantum information technology for, for the computation delegation with the privacy preservation. So those are three use cases selected. And then we were trying to have a section about the general requirements. Currently, we have three high-level requirements. The first one is a method for facilitating quantum applications to interact efficiently with the entanglement qubits are necessary. Actually, this requirement, I guess, by hearing to several simulator presentation, one of the, I forgot the name, I think this is also reflected in the current simulators, kind of API between the applications and the low-layer quantum layers. The second requirement is more like the quantum repeaters and the routers should support robust and efficient entanglement distribution. And then we have a third requirement here is more like we need to, even the quantum end nodes, they need to support the classical communications even for the CoKD and the quantum teleportation, the classical communications are required. It's kind of straightforward. But based on the feedback from mailing list, we add a to-do note in the document. Some performance indicators need to be defined and described, but in which level of those performance metrics we would like to cover in this document. It's a question for all of us. So in terms of next step, as I mentioned earlier, we have a few pending comments related to the control plan and data plan from MailQuire and MetaPass. So we're going to address this control plan and data plan application classification. We would like to also continue to collect feedback from the QIRG, from mailing list, and trying to improve the version 0.5. We also got two questions for the QIRG. The first question about the performance matrix in terms of in general requirements. I just briefly talk about that. The second question is, since we have received lots of interest feedback from the QIRG, so we were wondering and if this idea is ready for research group adoption or sometime later, or just trying to get feedback from the QIRG. That concludes my presentation. I'm open for any questions.
Thanks. Questions? We still have about 2 minutes here. Yes, question from Matthias.
Yes. The idea was just to answer the first question of Chung, which is how much detail. I think we should, in this document, it's a user document, so you should just explain, specify the things or word the things in a way the user would need it. I need something that is available with that level of probability. You need something that is that has a fidelity that is above that threshold. That is the way, and it may be like 4 or 5 quantities that for which you have to give a value, and that would be pretty much all.
Okay, yeah, we'll think about that, and also we can have a discussion via email or whatever. Yeah, thanks.
Thanks. Any other questions? I see we are at about 1 minute till, so we're actually running the meeting exactly on time. We did not set up any time slot in this particular meeting for sort of open mic discussion. I think overall this meeting's been a pretty good success running virtually this way. If you have open mic discussion style things, let's take them to the mailing list, including any feedback on the structure of the meeting itself. Also, I believe Wojtek is going to convene some interim virtual meetings to finish up the architecture draft as soon as the embargo on the smaller meetings is lifted, which should be soon. Wojtek, any final comments?
Just to reiterate, I think this was a good, successful meeting. Thanks for the attendance. I'm very happy to see all the activity in the simulators, and I think it would be great if people could slowly start. People here can slowly start picking them up for their own exploration and use cases. And it'd be great if people just shared their output on the mailing list as well.
Let's see. We have 65 names in the Etherpad as being attendees, so I think we've probably got everybody. If you did not sign in on the blue sheet on the Etherpad, please do so. That Etherpad will be closing. We'll be using that as our attendee list. And otherwise, we will see you all on the mailing list and hopefully in person sometime later this year, COVID willing.
Yeah, thanks everybody.
I think we're done. Thank you all.
Thanks, everyone.
Meeting now.
Thank you.